Hello, I'm Huizhong Chen, a PhD candidate in the Electrical Engineering Department at Stanford University. This video presents a summary of my PhD dissertation research titled Visual Word Recognition with Large-Scale Image Retrieval. In today's world, with the explosion of information, we are facing a fundamental challenge: how to process the huge amount of text data that's available to us. For example, the US Postal Service has to read 30 million envelopes per day to make mail delivery. Fortunately, with much of our life now computerized, we can rely on the powerful computing resources to automatically recognize text for us. This is called Optical Character Recognition, in short, OCR. One of the most common usages of OCR is the digitization of books. This video clip shows a linear book scanner developed for the Google Book project. The scanner acquires clean, high-resolution document images, which are then fed into OCR for text recognition. With modern OCR technology, people may naturally wonder if text recognition can be considered as a solved problem. Well, the answer is yes and no. If a scanned high-resolution clean image is passed to the OCR, the text can be recognized at very high level of accuracy. However, this goes against the current trend, as many text images are now acquired by a camera, in particular, a cell phone. When we feed a camera image to the OCR, the text recognition performance significantly degrades. The reason why OCR fails is because it recognizes text character by character. Unfortunately, character segmentation is extremely challenging in camera images due to view perspective distortions, uneven lighting conditions, the presence of noise, motion blur, as well as out-of-focus blur. This brittle character segmentation process, in turn, leads to a poor recognition performance. It has long been known from psycholinguistic study that human minds read word as a whole. For example, we can recognize this paragraph of words with scrambled characters without any effort. So why don't we build a text recognition system that also reads in words, instead of recognizing text character by character? I cast the word recognition problem as an image-based retrieval problem. We assemble a database of word patches, which contains large lexicon of words that are shown in many different fonts. During a query, the query word patch is searched in the database so that the word depicted in the query can be recognized. This large-scale image retrieval problem imposes a set of unique challenges. First, a good word patch feature must be used for robust matching between the query and the database items. Second, it is prohibitive to perform exhaustive search in the database. Therefore, smart system architecture must be used to speed up word recognition. Lastly, it is highly desirable to have a compact database representation such that the memory consumption can be reduced. In my dissertation research, I address these three challenges simultaneously. This corresponds to my three major contributions. First, I propose a novel word patch descriptor that accurately matches the query and the database entries. I then develop a visual font recognition algorithm that identifies the font of the query patches. Once the font is recognized, the system speed can be significantly enhanced, as we only need to search the sub-database that corresponds to the query font. Finally, I develop a compact database representation, which drastically reduces memory consumption while preserving word recognition accuracy. In this talk, I will start by reviewing related work, then talk about my 3 contributions in more details, and finally present an end-to-end text recognition system. This work focuses on text recognition, so let us first review prior work on text recognition. Conventionally, text recognition works on clean, high-resolution document images that are acquired by a scanner. This corresponds to the setting of OCR. Many OCR engines have been developed, including the open-source Tesseract OCR, as well as some commercial software like Abifine Reader, OmniPage, and XperVision. These OCRs achieve high recognition accuracy on scanned document images. As we mentioned earlier, with more document images now acquired by a camera, some research has been done to pre-process the image before feeding it to the OCR. The rationale is to make camera images look more similar to the scanned images for enhanced OCR performance. These methods include text rectification, image denoising, and image binarization. However, these preprocessing techniques are typically subject to document geometry assumptions and are sensitive to model parameterization, leading to marginal improvement on OCR accuracy. So in my work, I proposed a text recognition engine that allows robust identification of text in document images. In recent years, with the advances of machine learning, extensive research has been done to recognize text in the wild. This is called syntax recognition. There are 2 main approaches for syntax recognition. A popular method is a character-based approach. It applies character detectors in the image and then employs a graphical model to jointly infer the underlying word. Another emerging approach is to perform holistic word recognition. Go et al. Proposed dynamic time warping to match the syntax with synthesized words, while Rodriguez et al. Extracted Fisher vector features and performed word prediction using a structural SVM. However, we would like to emphasize that syntax recognition methods are computationally expensive. Hence, they are not suitable for recognizing document text that may contain hundreds of words per image. This work is about word patch retrieval. However, the idea of comparing word patches has been around for nearly 2 decades. Manmatha et al. Proposed the first treatment on word patch matching using template matching on binarized word images. Since then, other features that rely on binarized text were also developed, including stroke sequence string, horizontal and vertical text projection profiles, as well as feature sets that contain a variety of hybrid features. In recent years, with the popularity of gradient-based image descriptors, researchers also proposed the use of SURF, SIFT, and modified histogram of oriented gradients for word patch matching. Now, I introduce my first contribution, a discriminatively learned word patch descriptor. The basic idea is to learn the descriptor using actual word patches. The descriptor is trained using a large number of training triplets. Each triplet is denoted as XYZ, where XY is a pair of matching patches and XZ is a pair of non-matching patches. We wish to learn the descriptor such that in the feature space, the matching pair distance is smaller than the non-matching pair. I propose a novel word patch descriptor called Text Aggregated Gradients. in short, tag. The word tag descriptor is constructed in two stages, namely raw feature extraction and descriptor learning. Let us first focus on the raw feature extraction stage. Given a word patch, the gradient orientation and magnitude are computed. A set of spatial bins is densely defined over the word patch. For each spatial bin, an 8-dimensional gradient orientation histogram is computed. The concatenation of these gradient orientation histograms forms our raw feature of the word patch. In the descriptor learning stage, a set of sparse weights is trained to reflect the relative importance of these spatial bins. Let us more formally describe the training of word tag descriptor. Given a pair of features, fx and fy, their squared L2 distance is essentially the weighted sum of squared L2 distances from all the spatial bins. Let's visualize what's happening in the feature space, where we have the matching pair fx and fy, as well as the non-matching pair fx and fz. As mentioned above, we wish to make the matching pair distance smaller than the non-matching pair distance. In addition, we also add a margin such that the word patch matching can be performed more robustly. Without loss of generality, the margin is defined to be unit length. This corresponds to the so-called large margin criterion. We can formulate the descriptor learning as a convex optimization problem. There are two terms in the objective function. The first term is a penalization term, which adds to the cost whenever the large margin criterion is violated. The second term is a L1 sparse regularizer, which encourages a sparse solution to the learned weight vector. We optimize this objective function by seeking for a non-negative solution on W. We use 100 million training triplets to train our word tag descriptor. Each triplet is constructed using a synthetically degraded word patch, as well as its matching and non-matching clean word patches. We visualize the learned spatial bins by superimposing the non-zero weighted bins over a word patch. The weights of the spatial bins are color-coded, such that higher weights are shown in reddish color, while lower weights are shown in bluish color. It can be seen that all the learned spatial bins are concentrated in the middle portion of the word patch, indicating that the middle portion is more important in word recognition. To evaluate the effectiveness of our word tag descriptor, a word patch retrieval experiment is performed. We assemble a query dataset called Popular Words dataset, which contains roughly 13,000 words that appear in 16 common fonts. A camera phone is used to acquire these query word patches. On the database side, we use a large lexicon of 157,000 English words, where each word is rendered in 16 fonts. This gives a total of 2.5 million clean word patches in the database. We compare with two methods. The first is the well-known Tesseract OCR, and the second is a state-of-the-art word patch retrieval system based on word histogram of oriented gradients, in short, word hogs. The figure on the right-hand side shows the recall as a function of the number of retrieved words. Since Tesseract only gives one recognition result per word patch, it is plotted as a single data point. It can be seen that Tesseract and word hogs perform on par with each other. Since we use an English dictionary for word patch retrieval, for the sake of fair evaluation, we apply a dictionary lookup on the tesseract output. This improves tesseract by a few %. We now perform approximate nearest neighbor search using my proposed word tag descriptor. As illustrated in the figure, word tag significantly outperforms the other text recognition approaches. At top 1 word recognition, we achieve a performance gain of more than 8%. In the word patch experiment that we just described, the query word patch is retrieved from a database of clean words that are shown in 16 fonts. However, in real world, there may be hundreds or even thousands of fonts. Therefore, it is computationally expensive to perform an exhaustive search over the whole database. But if the query font is known, we can quickly eliminate a large number of irrelevant database items and only focus on search the subdatabase that corresponds to the identified query font. This gives much faster word recognition. I now describe a visual font recognition system that allows us to identify the fonts of query word patches. Here is an overview of the visual font recognition system. Given a query word patch, it is first split into individual characters. We then extract features from each of the characters. Since every character provides some cues for inferring the font, we combine the cues to make a joint font prediction. It is worth mentioning that, as we described earlier, character segmentation is a challenging task. Fortunately, document text usually has font consistency. For example, the same font may be used over a text line, a paragraph, or even throughout the whole document. Therefore, instead of recognizing font on every word patch, we make a joint font prediction over a set of query words. We now discuss the 3 steps of visual font recognition in more details. The first step is character segmentation. The basic idea is to look for shortest path that connects the top and bottom rows of the word patch, while avoiding text pixels. These shortest paths can be found by the geodesic distance transform. After computing the geodesic distance map, we look for the troughs in the map, which correspond to the spacing between characters. In the second step, features are extracted from each segmented characters. Ideally, these features should capture the variations of different fonts. We use the previously discussed Descriptor Learning framework to train the character descriptor, which we call the character tag. The matching pair comprises the same character with the same font, while the non-matching pair uses the same character but of different fonts. In this way, the character tag emphasizes on the variations between fonts instead of the variations between characters. As for the third step, we wish to combine the font information from all the characters to make a font prediction. A baseline method is the majority voting scheme. We use a toy example to illustrate this idea. Given a word patch, we extract features from segmented characters. We then perform a character retrieval by comparing against a database of character patches that are shown in different fonts. assuming the first two characters are recognized as members of font 1, and the third character is recognized as a member of font 2, then because the majority of characters vote for font 1, it is recognized as a font for this query. We naturally wonder if we can do better than this majority voting scheme. We realize that a character patch is essentially an observation of a character displayed in a particular font. Therefore, given a set of character observations, O1, O2, up to OM, with their underlying character labels C1, C2, up to CM, and a shared font label F, we can build a graphical model to capture their relations. Now, we can perform probabilistic font fusion by computing the posterior probability of the font given a set of observations. Using Bayes' rule and the conditional independence in the graph, we can derive the posterior as an expression shown here. The probability of the font and character given the observation can be estimated by softmax regression. Let's put font recognition in action. We assemble a query word patch dataset called the Wiki 100 dataset. The dataset contains all the 398 fonts from Windows 7 and Microsoft Office 2010. Each font is displayed in 298 most popular words, and we acquire the queries by a camera phone. Some sample word patches are shown here. Our goal is to recognize the font for each set of query word patches. The font recognition recall curve is plotted as a function of number of retrieved fonts. It can be seen that probabilistic font fusion offers a significantly better performance than the majority voting scheme. Additionally, we achieve 61% top 1 font recognition accuracy using the probabilistic voting scheme. Considering that many Microsoft fonts are visually similar, this is surprisingly good performance on font recognition. We take a step back and see how font recognition facilitates word recognition. Given a set of query word patches, the font is recognized first. We then perform word recognition using the subdatabase associated with the identified font. We conduct a word patch retrieval experiment on the Wiki 100 dataset. Once again, we compare with Tesseract and the Warthog approach. As shown in the figure, our font recognition plus word retrieval scheme greatly outperforms the other benchmark methods. It is also interesting to study how font recognition affects word recognition. Therefore, we also performed word patch retrieval using the font ground truth. Comparing the black and red curves, we can see that although our font recognition is imperfect, it only leads to a small degradation in word recognition accuracy. This is because even when we make a mistake in font recognition, the recognized font is still similar to the ground truth. Thus, it does not have a great impact on word recognition. In this experiment, the database storage requires 4.3 gigabytes of memory to host the words in these 398 fonts. It is highly desirable to develop a more compact database representation such that the memory consumption is reduced. I now present my third contribution, which comprises the database using canonical correlation analysis, while preserving the text recognition performance. We observe that some fonts have visual similarities. For example, the Arial font, shown in red, and the Helvetica font, shown in blue, share high degree of visual similarity, with their only subtle differences highlighted in the bottom figure. This motivates us to utilize these inter-font similarities for database compression. We use a two-step procedure for database compression, namely font clustering and feature aggregation within each cluster. We first introduce font clustering. The feature used for font clustering is concatenated character tags. This is a natural choice because the character tag is designed to differentiate fonts. Given a set of fonts, we perform k-means clustering to form groups of similar fonts. In the second step, features within a cluster are aggregated. I will use a toy example for illustration. Consider a cluster of 3 fonts, shown in cyan, yellow, and red. The database word tags are extracted for these 3 fonts, which are then aggregated into a shared representation. Once a shared representation is computed, the features associated with individual fonts are discarded, and we only keep the shared representation. In this way, assuming the font cluster contains k fonts, feature aggregation would reduce the size of the database by a factor of k. Perhaps the simplest feature aggregation method is to average database features over the fonts. This seemingly naive scheme turns out to be the optimum scheme for L2 nearest neighbor search in the original word tag space. This figure depicts the word recognition accuracy as a function of the number of clusters. The database is more compact as the number of clusters reduces. Compared to the original method where no database compression was applied, the descriptor averaging scheme suffers from a significant performance drop. This motivates us to look for an alternative method for feature aggregation. Consider the set of words in the lexicon. If we take 2 views on these words, they correspond to the 2 different font representations. We compute the database features for these 2 fonts. Since the fonts are dissimilar, the database features are also different across 2 fonts. However, is it possible that we look for a transformed domain such that the database features can be made more similar to each other? It turns out this can be solved by Canonical Correlation Analysis, in short, CCA. CCA seeks a set of linear transformations on the 2 views x1 and x2, such that in the transformed space, x1 and x2 are maximally correlated. After CCA transformation, the covariance matrix exhibits a simple structure where I denotes an identity matrix and D is a diagonal matrix, with diagonal elements equal to the cross-correlation coefficients. In our application, since many font clusters may contain more than 2 fonts, CCA must be generalized to handle more than 2 views. We follow Catering's approach, which trains generalized CCA by solving a generalized eigenvalue problem. This slide shows the procedure for word retrieval using a CCA-based feature aggregation. Assuming there are K fonts in the current cluster, we compute their database features and perform PCA for dimensionality reduction. These PCA coefficients are further transformed using the pre-trained CCA transformation matrices A1, A2, up to AK. The CCA coefficients are averaged to form the aggregated representation for this font cluster. During a query, it is important to note that font recognition must be employed to select appropriate CCA matrix for the query. For instance, if the query font is recognized to be the T's font, the T's CCA transformation matrix will be used to project the query. Now, with both database and query features in the CCA space, we perform nearest neighbor search for word patch retrieval. We return to the previous word retrieval experiment on Wiki 100 dataset. As illustrated by this plot, CCA feature aggregation offers a remarkably improved performance compared to the descriptor averaging approach. It is also interesting to note that when sufficiently many clusters are used, the CCA feature aggregation scheme even outperforms the original no database compression scheme, because feature aggregation adds extra robustness to the database features. In this figure, we show the word recognition accuracy for CCA feature aggregation using 20, 40, and 80 font clusters. Each accuracy curve is generated by varying the number of CCA dimensionalities. The no database compression scheme is shown as a sign cross. We see that CCA feature aggregation significantly compresses the database without compromising the word recognition accuracy. Up till now, we have described a word recognition method that robustly identifies words given query word patches. In order to implement an end-to-end text recognition system, we must also perform text detection and reading order analysis. Using connected component analysis, a dense text detector is implemented to locate words within an image. The detected words are then linked into text lines, where the text lines are labeled according to the page layout. Within each text line, the words are sorted by their reading order, according to the skew direction of the document. Having detected and sorted the word patches, we finally feed them into our word recognition system. Here, we show the actual word recognition results from our system. The recognized text is not perfect, but it is a large improvement over existing OCRs. Using a 2.4 GHz CPU, our current implementation takes about 130 milliseconds to recognize a word patch. In terms of memory, it requires 91 megabytes to store the words of 398 fonts, which gives a total of 63 million database items. To conclude, in this talk, I presented the 3 major contributions of my dissertation research. I first introduced a novel word patch descriptor that significantly outperforms existing OCR and word patch matching algorithm. I then presented a visual font recognition system by probabilistic fusion, we can achieve good font recognition performance and utilize the recognized font to help word recognition. Finally, I demonstrated a compact database representation that consumes far less memory while preserving word recognition performance. This is the end of my talk. Thank you for watching.